Okay, so how's everyone today?
Good.
Good? All right. So today's what, the 29th?
Yes.
October's almost over.
Christmas.
I think there's one, yeah, in between there, yeah.
Irrelevant. Just kidding. I like it.
All right, so then we were talking about functions, and we're still talking about functions. So, so in particular, last time we left with the following kind of idea. We said that for any given operation, we might ask, what does it mean to undo that? So to undo that operation, like hit the undo button. So to that end, we said, well, there's addition, and then there's this number that we call the additive identity. So what number is the additive identity? 0, because adding 0 is the same as doing nothing. And if I give you two numbers, A and B, how do you tell if they are additive inverses? If you add them together, and you get the additive identity. And then which numbers have an additive inverse? All of them, in fact. All of them do. And even better, we can just write from the get-go, we can say what the formula is. Given a number, A, what's the formula for its additive inverse? Negative A. You negate. So what is the additive inverse of 9? Negative 9. And what is the additive inverse of negative 6? Negative 6, right? Which is to say 6. Fine. Then for multiplication, what's the multiplicative inverse? I mean the multiplicative identity. You all said it right. So the multiplicative identity is 1, because multiplying by 1 is the same as doing nothing. And then if I give you two numbers, how do you tell if they are multiplicative inverses? Right, when you multiply them and you get the multiplicative identity. Right? And then which numbers have a multiplicative inverse? All of them except 0. So now multiplication apparently is more complicated because not everything has a multiplicative inverse. Right? Because there's no number b that would solve the equation 0 multiplied by b is 1. There's not a b you can multiply by 0 so that you would get 1. And then suppose I give you a number, how do you that's not 0, how do you compute its multiplicative inverse? What's the formula? So that, what you said, is to find perpendicular slope.
Oh.
So you're close. It's just reciprocal. So like, what's the multiplicative inverse of 2/3? 3/2. And what's the multiplicative inverse of negative 13 divided by 14? 14 divided by negative 13, right? Just reciprocal. Okay, so that's all cute and everything, but here's the deal: is that now we're actually talking about reciprocal. I mean, not reciprocal, about composition. So concerning composition, so in the first place, the composition identity is what? ID. And what kind of thing? What kind of thing is ID? Is it like is it a number or what? What kind of thing is it? Is it like a giraffe? No, it's a function, right? It's a function. It's not a number. So like the additive identity is a number, and the multiplicative identity is a number. But the compositional identity is this function. So in order to talk about it, we need to know its formula. So what is ID evaluated at x? formula of the identity function is you plug in an x and you get an x. So the identity function is the function where you put x in and x comes back out. You put a 5 in, 5 comes out. Okay, and notably, f composed with id, that needs to be f, and id composed with f, that needs to be f. So we have to write it down in both orders. We have to write it down in both orders because composition doesn't commute. Addition commutes, multiplication commutes, but composition doesn't. Okay, so then 2, you say that functions f and g are composition inverses when what? So how do you tell? Well, if we had two numbers and we wanted to check if they were additive inverses, then we would add them and check and see if we get the additive identity, right? So if we have two functions and we want to check and see if they're composition inverses, what do? We compose them and see if we get what? If we get the composition identity. But we have to compose them in both orders. Right. So like sometimes in like high school it's called fog, but I refuse to say that. I just refuse. Because in the first place, you can have functions that have names other than like f and g, for one thing. And if the names are like, if one of the functions' name was fr and the other one's name was g, then it would be frog. Okay, so I'm going to just avoid that. So now if we were to evaluate, since f composed with g is the identity, what does that mean? If we evaluate this function at x, what should we get? We should get x, right? And similarly, if we evaluate this one at any x, what should we get? X. Okay. 3. Now the question is which functions have a compositional inverse? All right. So then, going back to when we first started talking about functions, I could say, well, suppose we have a function defined with arrows like this. So domain with -2, -1, 0, 1, and 2, and range 0, 1, 2. And suppose that I do the squaring. So I'll just, so that should be not 0, 1, 2, but rather 0, 1, 4. So now suppose I do squaring. So that means that -2 will go to 4, -1 to 1, 0 to 0, 1 to 1, and 2 to 4. All right. So now suppose that that's some big machine there, and you're standing over here. And suppose that you witness a 1 come out of the machine. So suppose that you observe a 1 come out, but you can't, your colleague is over here, and you can't see them. So they do something, and suppose you witness that a 1 comes out. Do you know for sure what was put in? No, right? Because according to the rule, it could have been -1 was put in or 1 was put in, either one. So you can't tell, which means that you can't run this machine in reverse. You can't turn these arrows around. Because remember what the rule is that anything like this where you have domain and range and then arrows going, it's a function when there's always one arrow leaving. So is there always one arrow leaving these? Yeah, so there's always one arrow leaving. Okay, so it's definitely a function. And then have a look over here. Is it the case that there's always one arrow arriving? No. So even though it's a function, it is not what? Fishing for an I word that's not inverse. Starts with I. That one. Injective. So this is a function. So is it a function? The answer is yes, because one arrow leaves each element of the domain. And then is it an injective function? The answer is no, because more than one arrow arrives. More than one arrow arrives at some element in the range. So what that means is that if we were to make a copy of this machine, but take all of those arrows and make them point the other way, and so instead of pointing left to right, if they were pointing right to left, would the result be a function? It wouldn't be, because if the arrows were pointing right to left, then there'd be 2 arrows leaving 1. So it wouldn't be a function. So this function can't be turned around. So this is the kind of function that doesn't have a compositional inverse. What kind will have a compositional inverse? Right. So therefore, only injective functions have a compositional inverse. All right. So, that is to say, you could think of it like this. If I gave you 2 numbers and asked, do these numbers have an additive? Are these 2 numbers additively inverse? Then you just add them and check if you get 0. But if I give you 2 numbers, and ask, do they have a multiplicative inverse? Are these multiplicatively inverse numbers? Then the first thing you should do is check if one of them is 0. Because if one of them is 0, the answer is no. They couldn't possibly be multiplicatively inverse to each other. It's the same thing with functions. If I give you 2 functions and ask, are these 2 functions compositionally inverse? Then the first thing you need to ask yourself is, are they injective? If not, the answer is no. All right, so to that end, suppose that we say the following. Let g of x be 2x cubed plus 4, and let h of x be x minus 4 divided by 2, all of that inside of cube root. All right. So the request is determine if G and H are composition inverses? Okay, so what should we do? Well, if I gave you two numbers and asked you to see if they were additive inverses, what would you do? Add them. And if I gave you two numbers and said, are they multiplicative inverses, what would you do? You'd multiply them. And so I've given you two functions and asked, are they compositional inverses? So what should you do? You should compose them. All right. So we'll compose them in both orders. So G composed with H, evaluate at X. Okay, so then writing this without the composition operator is like this. And so now I'll write down the skeleton of G's formula. That is to say, everywhere I see an X, instead of writing X, I'm just going to write a big open parentheses there. So 2 multiply, I see an X, so thing there, and then cubed plus 4, like that. So now what am I supposed to put in that slot? Right, I'm going to put that, but first I'm just going to write this. That's what goes in there, right? So is there any question why that's what we've got to do? Okay, then now writing all that, so cube root x minus 4 over 2, cube that, add 4. So now, look at this crazy stuff that we're saying, that we're going to do. It's saying that, okay, take that x, subtract 4, divide by 2, and compute the cube root of that. And after you've done all that, I want you to cube the result, multiply by 2, and then add 4. Well, that's a lot of stuff that we're being asked to do with that x there. So let's see what that's saying. So is there any simplification that can be made? Which one? Well, it's not a square. Ah, you're saying the cube root and the cube, they cancel? Okay, great. So the cube root and the cube, they cancel. Like that. All right. Now, anything? The 2's will cancel. Amazing. No way. So what we're saying is that look at this crazy request here. That was, we said, okay, take that x, subtract 4, divide by 2, cube, and then compute cube root. And after you've done that, cube that, multiply by 2, and add 4. And that's all together a very long-winded way to say, take that x and do nothing. Just give it right back to me, please. All right, can you see all that stuff there? So as a result of that, that's saying that G composed with H, like that, is the identity. You give it an X, and it just gives it right back to you. So does that mean that they're composition inverses? Yeah, I got to check the other way, right? Got to check both ways. Okay. So H composed with G, evaluate at X. So that's G evaluated at H of X. And then writing down the sort of skeleton of, no wait, I did it backwards. H at G. So H's formula is kind of like this. So I wrote down, just what H does. And then what do I need to write in that slot there? Just G, right? So G of X. So that'd be cube root. And then 2x cubed plus 4. Subtract 4, divide by 2. Like that. Okay. So is there any cancellation can cancel anything? Well, in the numerator, if we drop those parentheses, then what? Then the 4's would cancel. Oh. So I'll do that. Anything else will cancel? Oh, the 2's will cancel, right? Amazing. Will anything else cancel? Oh, the cube and the cube root cancels? Amazing. So then, as a result of that, what does that tell us about H composed with G? Yeah, therefore H composed with G is the identity. So what's our conclusion about these two? They're inverses. So taking those two together, we can say therefore G and H are composition inverses. Understand that this is exactly like taking two numbers, and if I asked you if they were multiplicatively inverse, then you multiply them together and see if you get 1. So we're asking, are these two functions compositionally inverse? So you compose them, and in that order you got the identity, and then you compose them in the other order, and you got the identity. Therefore, they are inverses. All right. But here's the deal, is that one thing that I glossed over purposefully on this one is that I didn't even check if they had inverses. Okay, it turns out that they do, and they really are inverse to each other, but I didn't check it. Right? So then how about this one? Here's a question. So first question, I could say, does f of x equal to x squared have a composition inverse? So that'll be the first question. Okay, so then the next question, how about does g, where y equal to g of x is plotted below, have a composition inverse? And then 3, so here's this. Please plot y is the square root of x, and also please plot y minus 2 is square root of x minus plus 3. Okay. So question 1 there. So how about it? Does it have a composition inverse? What do you think? So which functions do have a composition inverse? Fishing for an I word. The injective ones, right? So the question does f have a composition inverse is equivalent to asking, is f injective? Well, is it? So again, it's the same kind of idea as that, like on that first page where you're standing on the output side of the building there. So what if we've got some big building that's the squaring building, and you're standing on the output, and you witness a 64 come out? Do you know for sure what was put in? You don't know. What could have been put in? an 8 or a negative 8. So the fact that you're not sure what was put in, you can't be sure, means that the function is not injective, which means that it can't be inverted. So what's the answer? The answer is no. So the answer is no, because f is not injective. Now we have to justify that, so we can just write down exactly what we said before. That, you know, what's f at negative 8? It's 64. And what's f at 8? 64. So the outputs are the same. You get 64 both times, yet negative 8 is not 8. So that's how you can say it algebraically. But another good way to say it is that, well, the plot of y equal to x squared is one of the plots that you're expected to know. So how does it look? You plot it? It's a parabola. And then when you've got a plot, when you've got something to look at, we've got a nice and easy way to check if a graph is the graph of an injective function. How can you tell? Which one? So the vertical line test tests if something is a function or not. The horizontal line test is once you've concluded it's a function, then you can check, is it an injective one? So like you know, this line right here. So to pass the horizontal line test, what is the maximum number of intersections allowed? 1. So notice that there's 2. So if this is y is 64, you know, so we're saying, you know, concerning the output 64, notice that there's 2 ways to get it. So what's this input? That's 8. And what's this input? Negative 8. So these 2 things are saying the same thing. All right. How about this one? Does this have a composition inverse? No, it doesn't. But wait a second, I have a question. What about this horizontal line? That horizontal line just has 1 intersection. I thought 1 was what we needed. But what's wrong with my you know, what's wrong with my statement? So I found a, you know, I know that the horizontal line test has something to do with horizontal lines and 1 intersection. So I found a horizontal line that has 1 intersection. Why is this not enough? It has to work for all lines, right? Not like your favorite line. Okay? For all of them. So, you know, here's one that has 3. So the answer to this question would be no, because it fails the horizontal line test. So it doesn't have a composition inverse. All right. So then what does the plot of this look like? It's not that one. That one, yeah. So it's like this. Looks like that. So this is something that you've just got to know. You've got to know these things. And so from here to here, right, this is a transformation. So notice that we're changing y to y minus 2. Because we're playing with the y variable, that means that there's some vertical thing happening. So what vertically is happening from here to here? What's going down? Okay, not exactly. So something is going down though. And what's happening is that the axis is going down. The graphite is going to go down. So it is like I hold my thumb on the red there, and I grab the axis and pull it down. So the axis goes down. Alternatively, something is moving up. What's moving up? The graph. The graph is moving up. So this right here, this is saying that the graph is going to go up 2. All right. So the graph is going to go up 2. And what about this? What's that saying? What's going to go to the right? Not the graph. So this is, yeah, the axis. The axis is going to move to the right. So what you're doing is you're saying, I'm going to take the whole axis and move it to the right. So that would be like, so I put my thumb there and I push the axis, bump, 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 and, push it to the right. So how does the graph move? To the left. So the graph is going to go left. Three. Okay. So, just looking at that there. So I'll color that one green, and I'll do this. So I want to go up 2. So 1, 2, and then left 3. 1, 2, 3. So that means that that green point has moved to right there. So the result looks like this. Something like that. So now, I'll just ask out loud, how about this one? This one right here. Does it have a composition inverse?
Yeah.
It does, because it passes the horizontal line test, right? So 0 intersection down here, 1 up there. Okay, so 0, 1. What about this one? Same deal, right? So both of these have a composition inverse. All right. So here's the question. I could say let p of x be 4 multiplied by x minus 2, square that, add 3. So let p be that. And let q be this. So q would be x minus 3 over 4, square root of that, add 2. All right, so we've got 2 functions there. And my question is determine if P and Q are composition inverses. So what do we do? Compose, all right. So then, fine. So P composed with Q, evaluate at X. So, this is pretty similar to that previous one, so I'm just going to race through this. So then P of Q of X like this. Fine. So this would be 4. And then slot there, minus 2, square that, add 3. And then the thing I'm supposed to write in the slot is Q. Okay. So 4 multiply square root x minus 3 over 4, add 2, in here subtract 2, square, add 3. Look at all that crazy business we're asking ourselves to do there. All right. So then, is there any cancellation that I can do? Ah, the 2's. The 2's will cancel. Okay, so suppose I cancel the 2's. That would give this. Okay, does anything else cancel? Oh, okay, that's great. So then they cancel. Does anything else cancel? Oh, amazing. And then this. Does anything? Oh, amazing. So then, look, this is like a really noisy way to say, take that x and do nothing. Do nothing with it. Just give it right back to me. Now, here's the deal. So therefore, P composed with Q is the identity. That's good. So have we established that they're inverses? No, we haven't, because what do you have to do? You got to do it in the other order. Now here's a foreshadowing of the punchline. We're going about this all wrong. Something is all wrong about what we're doing here. But with that being said, I'm going to continue now. So then Q composed with P evaluated x. So that would mean I want to write Q of P of x, which means that I would want to do this. So there's my slot there, and then minus 3 divided by 4 plus 2. And then what am I supposed to put in that slot? P of x. So this would be square root. All right, so then what goes in here is 4 x minus 2, square that, add 3, close the square parentheses, subtract 3, over 4, add 2. All right, so that's what we're saying we're going to do with that x there. So is there any cancellation? And I can drop the square parentheses, right? And then the 3's would cancel. We're getting close to the punchline here. So this would be 4 x minus 2 squared, because the 3's cancel. And then over 4 there, and then outside we still have this add 2. What else? Not yet, right? We got the 4's there, right? So now what? The square root and the square? What are they? What happens? What do I do with them? What? How do they combine? What happens when they? Do they cancel? So we're saying that whatever it is I'm covering up, we're going to square it, and then immediately after we're going to compute the square root. Do those cancel?
Yeah. No,
they don't.
Absolute value.
That's right. It's absolute value.
Wait, but you can square square root.
Yeah, you can do it in the other order. So this is absolute value of x minus 2, and then plus 2. So does that simplify? No. That does not simplify any further. Does not simplify to just an x. So what's our conclusion? They're not compositional inverses. Now I claim that all of the work on this page, in the first place, there should be absolutely no surprise that they're not compositional inverses. And furthermore, I also claim that you could have answered this question immediately without any of this work. Like this work wasn't even necessary. So I'll ask a different question. Suppose that you know how to multiply. I mean, you do know how to multiply, but suppose that you know how to multiply and it actually takes you an hour to do it. You know, just to say. And then suppose that I ask and say, are 0 and 8 multiplicative inverses? Then on the one hand, you could multiply them for the next hour, and then then check. But I claim that you can just answer the question now. Are 0 and 8 multiplicative inverses, or are they not? They're not, right? Because 0 doesn't have a multiplicative inverse. There isn't one. So because there isn't one, it's surely not 8. Right? So now which functions have a compositional inverse? Which ones do? The injective ones. The injective functions are the ones that have inverses. Are P and Q both injective? No, they're not. Which one isn't injective? Other one. Neither one of them have absolute value. So this one is squaring and that one is square root. Which one is injective? And which one is not? That one is not injective. Because, have a look. Suppose that we look at this plot right here. So what does the plot of y is x squared look like? Parabola, right? So is a parabola, is this the graph of an injective function? It is not. Now suppose that I draw another axis over here, and I say, okay, now please plot this one. Please plot y is equal to 4 multiplied by x minus 2, square that, add 3. But do it in the sense of graph transformations. Well, what I'm going to do is I'm going to take that equation and I'm going to get the y stuff with y and leave the x stuff with x. So I'll move this 3 over so that it's a y minus 3. And then after that I'll divide by that 4 so that it looks like y minus 3 divided by 4 is equal to x minus 2 squared. So now, x to x minus 2 means what do we do with the plot? Means right 2. Move the plot to the right 2. And y to y minus 3 means what do we do with the plot? Means up 3. And then dividing all that by 4, that means make it tall. So that means that the new plot is actually right there, and it's really tall. How about that red? Does it have a, is it injective? Is that red injective? No. So what I did is I asked you, are these two functions compositional inverses? And the answer is no, they couldn't possibly be, because that one doesn't even have an inverse. So can you see it? Good. So you should always check that. You should always check. One simple way to do it would be something like this. You could say, concerning the previous exercise, that function that didn't have a, that wasn't injective, was this 4 multiplied by x minus 2, square that, add 3. Well, let's plug in, say, like, what's a number that would make x minus 2 small but positive? What's something we could plug in? 3. Okay. So then p evaluated at 3, that'd be 4 multiplied by, what's 3 minus 2? That's 1. Square that, add 3, and then you do that carefully and you get a 7. Is there some other way we could get a 7? we made that 1. To get a 7 a different way, we'd need to make this a negative 1. How can we make that a negative 1? We do 1. And what's that? 7. So that's saying that if you, for that P, if you witness a 7 come out, do you know for sure what was put in? No, it could have been a 3, or it could have been a 1. So that P is not injective. Okay, any question about this one? So now, notably, there's one notable item missing. So, if I gave you a number and said, find the additive inverse, then the way that you calculate it is by negating. And if I give you a number and say, find the multiplicative inverse, then the way that you calculate it is by reciprocal. Now, what we're going to do is I'm just going to write something down. I'm not going to do any calculation. I'm just going to say what we would do, and we're going to do it first thing next time, is what if I gave you a function and said, find the composition inverse? Okay, so the way that you do it. If I say let, for example, f of x be, 7 multiplied by x cubed plus 4. Find the composition inverse. Well, the way you do it is like this. The first thing you do is you write, just write exactly that function. Then you write y. So exactly the same thing except y there. And now you do a bunch of steps, and you need to solve for x. So notice that y is currently solved for, and you're going to have to pull every algebraic trick out of the book that you know to solve for x. And we're going to do that next time. So have a nice Monday.